let's see, let's go back to King Julian, but not for King Julian. For relevant reading materials, I think you may want to read chapters 1 to 4 in Zemansky, but there's whole sections of chapter 1 that deal with definition of temperature and how to make all kinds of thermometers. You can skip that, it's a bit old style thermo. But it covers essentially what I'll be covering in the next couple of lectures, things like heat and work. And then I really also like Defontaine's book. And there, Defontaine's a little briefer. I have a copy here, Principles of Classical Thermodynamics, but it's sort of more mathematically rigorous. And if I were to buy one book on classical thermo, I probably would buy that book. And if you feel a bit rusty, like on concepts of ideal gases and equations and how to manipulate them, you may want to just read on that. And that you can find in any undergraduate thermodynamics textbook or any physical chemistry textbook. Okay, so then let's get started. So I gave you a bit of introduction and history last time. And towards the end, I'll give you a little more history, but for now, I sort of want to delve in. So if you remember, the major concept of thermodynamics is that we will track energy flows across the boundary, and that somehow will lead to an optimization criteria, so equilibrium. So one of the things we're going to do today is figure out how we quantify those energy flows. The first thing I want to do, though, is state the first law of thermodynamics, which is the conservation of energy. Which is generally true in all but a relativistic sense, right? So there is a version of this that includes relativity, but for our typical world, this is always true. And it's a fairly straightforward statement, right? The statement is that if you have some system, and if you keep track of all the energy flows across the boundary, so going in and out, that if you take the balance of those energy flows, because energy is conserved, that has to be the energy left into the system. So typically we will that makes sense because then it adds to the energy of the system, but just be aware that in some cases it's done a little differently. For example, often in mechanical engineering, they state work as an energy flow that's positive when it comes out. And that's because they're often interested in machines that produce work. So the positive quantity is what you want. But our definition is that it will be positive going into the system. So then the first law is simply a statement that the energy change of a system is the sum of all the flows, right, across the boundary. I know I could label it, where you state positive is going in, negative is going out. This is a conservation law like many other ones you've seen. For example, if you studied heat transfer, you would have seen conservation laws like that. If you study mass transfer, you would have seen, like diffusion, you would have seen conservation laws like that. They're usually written in a more mathematical form. So, for example, if I develop diffusion equations, I would have some where I'm transferring some mass. I would write something like the mass per unit volume in some volume element. The change of that per unit time is minus the divergence of the mass flux, right? So this is a conservation law for mass, but written in more mathematical terms. So if you don't like this macroscopic way of writing the first law, I can give you a more mathematically refined way. You could simply write this as the energy divided by the volume, so the energy density, the derivative of that in some volume element with time is minus the divergence of the energy flux. Right? So this is also the first law, right? Because it's a statement of conservation of energy. Why do you always see the divergence of fluxes show up here? It's because what does divergence measure, right? Divergence measure how the flux changes. So let me give you a one-dimensional example. Let's say I just have a one-dimensional example where, you know, this is a coordinate x, this is x plus dx. So here I have the flux jx, here I have the flux j at x plus dx. So if I want to calculate what the net amount of stuff left behind in this volume element is, right? So I calculate, well, jx is what's going in, j at x plus dx is what's going out. So this thing is the balance of what remains in. This I can tailor expand, right? This is, so I'm going to write this as jx plus djx dx times dx, right? And so these two cancel. So what I get per unit, so I get something here, right? dt is going to be minus djx dx times dx, but if I do it per unit volume element, this goes away. So in conservation laws, you always see the divergence, divergence show up, because what is the divergence, right? In general, the divergence of a flux of anything is dj djx dx plus djy dy plus djz dz. So it essentially tells you how the flux changes as you traverse a volume element. And again, when the flux changes, the flux of a conserved quantity changes, it has to be left behind in the volume element, right? Okay, so you could just think of the first law as a conservation law that you've seen well before. So when we leave energy in a system, so let's say this is our system, how is it stored there? So the question is, what are the contributions to the energy of a system? Typically, we divide them in three parts. You could increase the kinetic energy of a system, right? You just change its velocity. You could move it in some field, so that would be changing its potential energy. That could be a gravitational field if you have mass. That could be an electric field if you have charge, or other things, right? And then the third one is the internal energy. And this is sort of a cop-out in thermodynamics. And it has to do with the fact that thermodynamics can make no statement of what's going on inside. So there may be various mechanisms by which you can store energy inside a system, but because we don't do atomistic stuff, or we don't use an atomistic description, we can't actually quantify, well, we can quantify, but we can't actually attribute that. So if you had a material, you could say, well, I'm putting energy in the vibrations of the molecules, but thermodynamics is only a macroscopic theory, so it calls all that energy internal. So this is in contrast, say, to physics. If you do physics, right, there is no concept of internal energy. All energy is attributed to some degree of freedom, you know, dipoles or bonds or kinetic energy of atoms. But again, in thermodynamics, we actually can't do this, right? So this concept is needed because of the macroscopic nature. So I want to do a small example to see how well you've listened. Here's my friend. Can you see my friend? His name's Calimero. Calimero is a cartoon character from many, many years ago when I was this high. So his name is Calimero. And normally I would do this with a volunteer in class. Calimero has a little spring on the back. Yeah, you know, you have to believe me, right? It's one of these wind-up toys. So I'm going to wind up Calimero. And so I'm applying an energy transfer to Calimero, right? Because there's clearly, I'm doing rotation times torque. So I'm clearly putting in energy. So let's write the energy balance of Calimero. Here's Calimero. I should make him look cute, right? He's a little fat, but wobbly feet. I'm not very good at drawing. You'll find that out very soon if you haven't known. Okay, here's Calimero. So what did I just do? I put energy in, right? And we'll later see that that's work, because what I did was torque times rotation, right? Which is the equivalent of force times displacement for rotation. Where did that energy go? Since energy is conserved, where did that go? Okay, I can't go forward if I don't have an answer, so somebody's going to have to answer.
Potential energy of the spring.
I'm going to have to load. I'm going to have to set up some speakers here. Can you repeat?
It goes into the potential energy of the spring.
Okay, cool. That's exactly the answer I wanted, because it's not the right answer. Well, it's right and wrong. We'll see. Does anybody want to correct that answer?
It's internal energy.
Yeah. You can only call it internal energy. I mean, you're absolutely right, right? If I smashed Calimero, which I'm not going to do because I like him, you would see that there's a spring inside. But the truth is, in thermodynamics, we don't know. In thermodynamics, we look at Calimero as a purely macroscopic object. And all I see is that at the boundary, I'm doing torque times rotation. So that energy went in internally, and I agree with you that your assumption, you made an assumption about how it's stored internally, that it's a spring that's wound up, but we don't really know, right? You know, there could be a battery inside, and I'm like, you know, driving a generator that charges the battery. We actually don't know, right? And that's how you have to think about thermodynamics. Okay, so let me use that stored energy. Maybe the camera can focus. So I'm going to let Calimero go. He's going to walk off the... Oh, well. Come on, dude. Okay. I hope you could see Calimero walk around. So what happened now? If we think of the energy balance, come on, dude. He doesn't want to stop. Okay. He's in my couch now. So in the first step, step one, we put work in, and that led to an increase of the internal energy, right? In step 2, what happened there? In step 2, the internal energy decreased, and that got converted to kinetic energy, right? In a very imperfect way. And then he stopped, so he kind of dissipated the kinetic energy. Okay, so here's an example of how you should think. So I kind of solved this problem, although solve is an overstatement, just by looking at what happens at the boundaries of Calimero. I don't really need to know that it was stored as a spring, right? Okay. Most of the time, we will deal with stationary systems. So that's good because we don't have to deal with kinetic energy. Occasionally, we will come back to it though. And then again, often, but not always, we will also not deal with systems in a field so that we don't have to deal with potential energy. But again, sometimes this comes back, right? So sometimes we will move something in a gravitational field, or we will move a charge in a electrostatic field, and in those cases, this will become important, right? Okay. So the way we're going to work through this is, first we're going to talk about all the ways you can transfer energy across a boundary and how you quantify them mathematically. So energy flows or energy transfers in thermodynamics are divided as work, heat, and matter. So those are the 3 different ones. Matter is sort of the trivial one because transferring energy as matter is simply the joining of systems, right? If I have a system and I'll call it alpha and I have beta, you know, alpha could be my car and beta could be gasoline, except I have a plug-in hybrid, so it's often electricity. But if I fill my car with gasoline, I'm basically just joining, right, beta into alpha, but that is a transfer of energy. So if you're a mechanical engineer, you've dealt with this many times because when you deal with pumps and compressors and you constantly deal with material coming in and out of a system, which is a form of energy transfer into the system. And there, the way you address that typically is with enthalpy balances, and we'll show just a tiny bit of that later. Okay, so let me talk about work. So work usually has the form that it's the energy transfer resulting from a displacement, a generalized displacement, not necessarily a spatial one, I'll come to that, under a force. So under action of a force. So, you know, you have mechanical, right? Mechanical is something like F dotted into the R, right? So force times displacement. Remember, force alone is not enough to transfer energy, right? You need displacement. You have electrical, which you could write as, say, a potential over which you transfer times the differential charge. So if I, you know, transfer a charge dq from, say, 0 to a potential, right? That I'm doing work or receiving work. Then I'm transferring energy into that system. Okay, and then of course you have magnetic, and we'll come to that later, right? And magnetic will look something like mu naught h dm. right? Where M is the, where H is the applied field, M is the magnetization, but we'll come to this in a bit. Sorry, I'm making the same mistake. I should stand here so you can see this board. Then how do I erase? Okay, I want to work these out a little more in detail. So in general, a work term looks like y dx, where y is some kind of force and x is the response to that force. A pair of variables, y, x, that appears in a work differential, this is called a conjugate pair. And their units, so the product of their units is the unit of energy. Right? So if I do F dr, I have Newton times meter, right? So that's joule. If I do potential times charge, right, I have volt times coulombs, so that's also joules. Okay? And let's not get into magnetic units. I still can't figure them out. Okay. Okay, so let me work out one of the mechanical differentials more. So I'm going to look at deformation of a material at the boundary. Okay, so in general, if I have an arbitrary state of stress, you would represent that by a stress tensor, right? So you would have diagonal components. So you could call them sigma 1, 1, sigma 2, 2. And then in the third dimension, right, you'd have sigma 3, 3. That's the x, y, z directions. And then you'd have the shear components as well. So you have a general stress tensor, sigma 1, 1, sigma 2, 2, sigma 3, 3. And then you have the shear components, sigma 1, 2, sigma 1, 3, sigma 2, 3, whatever order you'd like to write them in. And then you have the strain components that are the response to this. Epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, epsilon 1, 2, epsilon 1, 3, epsilon 2, 3. Okay. So in general, the work done on a system is the volume over that the boundary spans times the stress tensor dotted into the strain tensor. Okay, because you can work out where the volume comes from, because force would be area times the stress, and length, right, would come out of the strain. So that's how the volume comes up front. So if I know the stress state at the boundary of a system, and I know the response to it, I can actually calculate the work. So you can simplify this often quite a bit. So a simplification comes when you have a system under hydrostatic pressure. So if you have hydrostatic pressure only, right? Because in that case, so hydrostatic pressure, so you have just pressure applied everywhere. Because in that case, the pressure or minus the pressure is the normal, are the normal components of the stress on the surface. The minus comes from the convention issue, right? That in mechanics, stress is defined positive when it's tensile, but pressure is defined positive when it pushes on something, when it's compressive. So, right, that's why you have the minus sign, right? Okay, so if I only have the normal components, then this expression here for work simplifies, and now the work is minus P times the volume times the differential of epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. And this here together this is the differential change in volume, right? The reason is that the variation of the normal elements of the strain, this is the relative volume change, and then you multiply with volume, so you get dV. So what you find is that dW is minus PdV. And I'm sure you've seen this many times before when you did undergraduate thermodynamics. This is the work that a system does in a pressure field when it's changing its volume. And because of that, this is actually a work term that's almost always present in thermodynamics, because we don't control the volume of systems. We control the pressure on systems. We tend to live in a 1 atmosphere pressure environment. But when I do stuff to materials, they might change their volume. For example, let's say I heat it up. It would change the volume, right? So this work term is kind of always there, even though you don't explicitly think you're doing work on a system, right? The sign makes sense, right? Think about this. P is always positive. So if I expand my volume, so dV is positive. So imagine I'm a system, I'm becoming bigger, I'm pushing against the environment, so I'm transferring energy to the environment, right? So the energy flow is negative, it's going out. If I shrink, then the environment is doing work on me, so I have energy delivered to me by the environment, okay? So the sign makes sense a lot, right? So in some cases, this becomes very important, right? When you do things to materials that cause large volume changes. An example is boiling, right? You never think of boiling as delivering mechanical work to the environment, but you do, right? So when you take water and you evaporate it, the volume goes up, I think, by a factor of 1,000 or something like that, right? So when you boil water, it's not just, the heat you have to put in is actually not just to break the potential energy, to break the bonds between the water. Actually, about 20%, if you do the calculation, is actually to do this. 20% of the heat of boiling is actually simply to make your system bigger in the environment, which is, by the way, why the boiling point has such pressure dependence, right? Later, we'll actually have you calculate this. But in most cases, volume changes on materials are actually quite small. Okay, so if you want to, this is a differential equation, right? It's a weird one, right? Because it's not one we can solve right away because we have W here, we have P, and we have V, right? So we have 3 variables, and to solve a different equation, there should be 2 variables, right? One on the left, one on the right. So to actually solve this, you usually need some information about the material. So if I wanted to integrate this differential equation, minus PdV, what would I need about the material? I would need a relation between P and V, right? So this is a general statement, but to actually get numbers, I would need to know P as a function of V or V as a function of P. And so this is defined as a property of materials. So the way the property is defined is the derivative of volume with respect to pressure, right? And it's normalized by the volume, right? Because this is an extensive quantity, V. With properties, you don't want to depend on size, right? So I normalize by V. And because this is negative, right? When I push on something, it becomes smaller. So this is defined with a minus sign. And this is called beta T. So I take this at constant temperature. And this is called the isothermal compressibility. Right? And we will see this every time that when we want to integrate a differential, we need to understand the relation between the response of the material and the applied force, right? And we will not be able to do that without materials information. So in general, if I went back to the generalized mechanical work term, what would I need? What would I need to integrate this in general? I would need the compliance or the elastic tensor, right? Because I would need the relation between all the sigmas and all the epsilons. So in general, you would need that. So how would you define compliance? So Ci, J, K, L. There are now 4 indices on compliance because I have 2 on the stress and 2 on the strain. Would be something like the epsilon ij, the sigma KL, right? And taken at constant temperature, right? So the compressibility of a material is obviously some integral over that. It's some combination of all the elastic constants, right? Right? Because they give me the same information, but the compliance tensor or elastic tensor is the inverse of the compliance tensor, right? Gives you the full mechanical response. Okay, let's keep on going. Let's say I do electrical work. So now I'm transferring a charge, dq, over a potential difference. So my work is phi dq. So what's the property I need to know now to integrate? Here I'm going to wait till I get an answer and I have my coffee. Sound is on. Jen Yang, maybe we should pick randomly people. No, that would be mean. Okay, what relates electrical potential, so voltage, to charge on a system? That's the capacitance, right? Right? So what you would want to know here, right, is you would want to know like how potential changes with charge, constant temperature, right? Or the inverse derivative, how charge changes with potential, right? And what is this? I mean, this is the capacity of a capacitor, right? This is the capacitance. So what I'm trying to show you is, right, that all these things that you've learned independently, right? When you've learned about electricity, somebody talks to you about the capacitance of a material, right? The capacitance plays exactly the same role in thermodynamics for electrical work as the elastic tensor or compliant tensor or the compressibility play for mechanics, right? These are completely mathematically equivalent concepts. And this is what I told you in the beginning, right? So in thermodynamics, all this stuff is going to be on the same footing. We're going to integrate all these things together, right? So every time I have a work term, there's a property of the system I need to know to actually do the integral. The electrical one can be a little confusing. So because it's sometimes written in terms of dielectric language. And I want to show you the relation because they are just a different perspective. So dielectric work is really another perspective on electric work. So let's say I have a capacitor. Right? So I build up some potential here between the plates, right? And in here is a dielectric. So I have an electric field in here. It's technically a vector, but if this is sort of a one-dimensional capacitor, then it's just a number, right? And I'll give this thing a length. So if I take as my system this outside boundary here in dashed red, and then I sort of do a perturbation dq, d phi, change the potential. What's the electric work? Again, the electric work is what's performed on the boundary, right? So all I see is that if I change the potential, there might be some extra charge flowing dq. So at that point, the work I do is phi dq. But if I now take an internal perspective, right, and I actually look at the dielectric itself, so I try to figure out now, I move my system boundary inside, so I actually don't see the charge flowing. Then I'm going to see things like changes in electric field and so, right? And so if I translate now what these are, this here is the electric field times the length over which it operates, right? Potential is the integral of the electric field over length. So here that's just E times L. Charge in capacitor language, right? This is the area times the change in what's called the displacement, right? D. And so when I look inside the dielectric, my work term looks very different, even though it has to be the same. So I have L times A, so that's volume, right? I get volume, and then I get electric field times the differential of the polarization displacement. Okay, and now when you do dielectrics, then the polarization, the polarization D is usually written as the contribution from vacuum, so the permittivity of vacuum times the electric field, plus P, and P is the induced polarization in the material. Let me write that out. Now that means I have V times the permittivity of vacuum, EdE, plus V times epsilon times E dP. And so that is now the work done. So this work is the same as that work, right? It's just a different perspective. Think of Calimero again, right? If I didn't tell you that this was a dielectric inside here, and I put this in some kind of box, all you see is phi dq, right? You see charge flowing in over a potential difference. That's all you know. If I start making statements about what's inside, then I know it's a dielectric, and I know that that energy is stored by polarizing the material, et cetera, right? So these are the same energy flows, but taken a different macroscopic description. Now, there's a few other things you have to notice. The first term here is independent of the material. So this is, because this is just EdE, this is the dielectric constant of vacuum, and this is the volume that's filled by the field. So if I had no material in the system, if this were empty, I still have that term. So that's why sometimes this is called the energy of the field. Because it would be there even if I didn't have a material. And then the contribution that's stored in the material comes from this term. Right? Because here I have a P is the induced polarization in a material, right? So I apply an electric field. If I have a dielectric, I induce a polarization. So this is the energy. So by the way, I know this is confusing. This is field, right? And then I write E, but this meant energy. I'll write it out. So this is energy in the field, and this is energy in the material. And most of the time, we're just going to worry about this piece because this piece is fully reversible, right? This just, if I switch off the field, this comes completely back. This can get absorbed. There's a few other things you should notice, and this is more of a nomenclature thing, notation thing. So when you did electromagnetism and stuff and dielectrics and you did whatever, you read the Feynman lectures or whatever, these quantities are, in electromagnetism, they are defined by per unit volume, right? If you look at their units. But in thermodynamics, we care about extensive quantities, and these actually play the role of extensive quantities. In electromagnetism, they are normalized by volume, so they're what we call densities. But here, you will see in thermodynamics, if you write them as a density, they will always show up with a volume in front. So sometimes I'm going to make a shortcut and put the volume in the quantity, and I'm going to write shorthand that's going to look something like dW is epsilon naught E dP. And sometimes I write a curly P, and the curly P is really, no, that looks like a sigma, right? Is volume times P. But I'll tell you, most of the time, I don't care, and I'll just write the P. Okay? Just keep in mind that in thermodynamics, our displacements, which, right, the results of the forces are extensive. So when I write P, I'll very often just write P, but it's implicit that the volume's in there. And you will notice this in the end when you do math, because you have to check your units, right, that you're missing a whole volume. if you just use fields. The other thing I don't like, I don't care about epsilon naughts and mu naughts. So sometimes I just work in arbitrary units and I'll get rid of that. So this is great when you just do formal derivations. But of course, when you start plugging in numbers, you're going to have a major problem, right? That this actually doesn't lead to units of energy. So you have to remember that epsilon naught is there, okay? And I'm going to do that even more with magnetism because there's way too many weird units in magnetism. And we do that to keep the math of derivations as simple as possible. So I guess what I'm telling you is that I might write this, I might write this, or I might write this, and they're all the same, okay? Here I wrote the volume explicitly, here I dropped the epsilon naught, and here I dropped the volume, okay? And if you have questions about it, just ask me. Okay, the last one I want to briefly mention is the painful orphan of all this, which is magnetic work. In magnetism, right, you call H is the applied field. B is called the induction, which is mu naught times H plus mu naught times M. And B is called the induction. And by the way, this is really annoying, right? People should have gotten their units straight, right? So in magnetism, they multiply to get the response in a material, right? B, they multiply the field and the response with mu naught. Whereas in dielectrics, they don't, right? D is epsilon naught plus P, and the epsilon naught is not multiplied by P, right? And it's because these fields developed independently of each other, right? It's very annoying, but anyway. So the work that's done by a magnetic field is the volume times H mu naught dH, if you do the exact same derivation, plus mu naught times H dm, where m is the resulting magnetization in a material. I didn't say that. So this is the magnetization in the material. And again, what you see is that, oh, I forgot a V, sorry. I forgot a volume. Same deal again. This is stored in the field. This is stored in the material because the response function is in the material. Similar problems, the V is written explicitly because in electromagnetism, magnetization and applied fields are written as per unit volume. They're written as densities. In thermo, because we want to get to extensive quantities, we will often morph these together and put V inside there. And then occasionally I will drop the mu naught as well and work in my own units. So occasionally, just to go fast, I might write dW is just H dm. Okay? So these are the same expressions, right? I've just assumed different units for H and M. Okay? But it's sort of a shorthand when we look at pieces of physics or derivations. Okay. What's the materials parameter that you need to know to integrate this? So let's say I start applying a field to a material and the magnetization goes up, right? So I need some materials parameter here, which is going to be some derivative, right? It's going to be something like dm dh, right? So it's going to be something like dm dh normalized by volume, or depending on if these are both written as extensive, then so normally this would be intensive, this would be extensive. So the parameter would be something like that. And that's a magnetic susceptibility, right? Again, it's the response function we need to use for magnetism. Okay. Last thing for today is difference between exact and inexact differentials. For now, I've been kind of sloppy, but normally if you write a straight D, that's an exact differential. An inexact is written with the Greek delta. This is an inexact differential. And we'll show you in a bit that that the work differentials are inexact, which is sort of a major issue in thermodynamics. So if I give you a differential, say FDR, how do you know whether it's exact or not? The definition of an exact differential is that it's the differential of a function. So that means there is a function exists of which this is the differential. And of course that implies that f has to be the gradient of that function with respect to r, right? So if I have some function of r and f is the gradient of that, then f dr is an exact differential. So if I write that out more, what that would mean is that f of x would be the derivative of the function with respect to x at constant y, and f of y would be the derivative of the function with respect to y at constant x. Some consequences of being an exact differential. If I'm boring you, just hold on 5 minutes. You'll see that this is not that obvious. So the consequence of being an exact differential is that if you integrate an exact differential between 2 points, so I integrate f dr between 2 points, well, that is the integral of the gradient of the function right? Because that's my statement. If it's an exact differential, this has f has to be a gradient of something. So that is phi r2 minus phi r1, right? So if f is the gradient of a function, so if f dr is exact, then f is called conservative. And the reason it's called conservative is because when you integrate it in a circle, so if you integrate in a trajectory where you start in a point and you come back to the same point, then of course the integral of f dr is 0. Right? So when that differential operates in a loop, it produces no net energy transfer. Okay, that's a conservative force. So I want to show you that it's actually not that obvious that physical differentials are exact. So differentials that describe real physics. This is all easy to say in math, but this was a problem that lasted about 200 years to figure out when you actually apply this to thermodynamics. So I'm going to do this with a toy example. What I'm going to do is I'm going to move an object in a potential energy field, let's say a gravitational field. And first I'm going to do that perfectly, in which case we will have conservative forces, and then I'll show you where the imperfections come from. So let me do an example. So imagine that I have some kind of potential energy landscape, and I'm going to draw it by contour lines. So think of this as a topology map, right? If you've ever hiked, you know, you have a topology map, and so I have contour lines, right? You know, maybe like this, and there's a ridge here, and I don't know, whatever, right? And I'm going to move from one point to another. Say this is point 1, and I'm going to move to point 2 here along some trajectory. So let's say that this is a gravitational field, right? So, and I'm moving my car in there. So if these contour lines were to go down, I mean, you know that I would pick up speed normally, right? Because gravitational energy would work on me and accelerate me. But I'm going to have the perfect hybrid car. So I'm going to go very slow, and whatever energy comes from the field that wants to accelerate me, I'm going to gently brake and absorb that in my battery inside, okay? So I'm going to do a perfect transfer between the gravitational field and my internal energy. So let me work through what will appear as some trivial calculations. So I'm going to calculate the energy transfers. And I encourage you to do this because it will look trivial, but it sort of will force you to think very rigorously, which is kind of what you need in thermodynamics. So, so the energy of my car or whatever my object is, so the potential energy in the field, in the gravitational field, as you know, is mgh, right? And h, the height that I'm in the field, is a function of x and y. So let me now calculate, as I move in that field, let me calculate what delta U is of my system. My system being my car that I'm moving. Okay, so work is being done on my system. So delta U of my system is going to be the total amount of work done. And what's the work done? That's the integral of f dr between points 1 and 2. Right? That's the work done. And the force, right? Gravitational force is minus the gradient of the field. So this is equal to minus the gradient of the field energy times dr between 1 and 2. And I know what the field is, that's up here, right? So I can take the gradient of that and then I can integrate this. So what do I get? I get that U2 minus U1 is equal to minus mg H2 minus H1. Okay. And of course you could have guessed this, right? I don't have to actually do all this math because what I'm giving here is the change in potential energy of the field, right? My potential energy in the field has changed, and that has to be absorbed as internal energy. And the energy of the potential energy in the field plus the delta U of the system remains constant, right? So that change is zero because this is mg H2 minus H1 minus mg H2 minus H1. Okay. Now by now you're probably going, why the hell is he doing this at 9 o'clock in the morning? This is so simple and it confuses me even more. Well, let me show you now that this is actually a rare exception. And what really goes on normally is a sort of different story. So the question is, how do differentials become inexact? Because then you cannot do all this clever math. So how does a differential become inexact? An obvious way is if you're missing forces. Basically, you don't have full understanding of your system, right? If you're missing ways that the system transfers energy, so let me give you a very trivial example. Let's take our contour space again, so x, y. And I'm just going to simplify it a bit, so I'm going to make the contours, make this very simple ridge where it looks like this. And then the last contour just follows this. Right? Okay, so let's say my physics is not very good. I went to the wrong school, and I actually, you know, instead of integrating the total force, I think that that the differential of work is just the integral fx dx, right? I didn't pay attention and I forgot the fy dy in class. So now let's integrate along this path. I'm going to call this 1. Right? This is path 1. What is the work along path 1? Think about that. I feel like we should be doing polls. Okay, there's 2 pieces to the path here. When I go up here, the work is 0 because there's no dx, right? So when I go this way, I have dx, but I have no force because there's no gradient, right? So I have no force in the x direction. So the work along this path is 0. Now what about the work along path 2? Is that 0? So let's take, oh, I didn't tell you what path 2 is. Darn. Okay, let's say this is path 2. Oh, this doesn't write. This is path 2. Is the work 0 there? Not at all, right? Because, so here I have both a dx, and because I'm going, let's say I'm going down, right, here, I'm going perpendicular to the contour line, there's definitely a force. So here I'm definitely have work, but here I don't have work. So along this path, the work is not 0. So by forgetting part of the forces, by doing bad physics, my differential became not exact, right? So this differential is not exact. And it's also sometimes more simply stated as not complete or not total. Those are basically the same statements. A second way that you get non-exact differentials is if you have dissipative forces. Friction would be an example, right? For example, let's say I wrote my force as minus the gradient of the potential energy. So that's the normal conservative force. But let's say I add something that's like minus some number that I'll call F, that multiplied by the unit vector along the velocity direction. So this is the unit vector. That's just so that it gets some, I just need this to put the force in the right direction, because this is the unit vector along the path, right? You can see that if I integrate this, right? If I now integrate del W, so it's the minus the gradient dr minus F times dr. And so if I integrate that, right, what do I get? I get mg h2 minus h1. And then I get here minus F times the length of the path integrated. So that's just L, where L is the length of the path. So that's W. And this is by definition path dependent, right? Because I've put the length of the path in there. So there's definitely not going to be a conservative force, right? If I go around in this landscape between 2 points, the conservative part of the force will 0 when I go around, but the length will keep on adding every time I go in a loop, right? This term is non-conservative, right? Okay, so how does this apply to thermodynamics? I need a prop. I think in mechanics, most of the time you learn that forces are conservative, because it allows you to do all kinds of tricks, right, to calculate mechanical equilibrium and so on. But let me give you an example. Here's Desfontaine's book. I'm going to push my hand on it, and I'm going to rub back and forth. Okay? Was that a conservative force? If I went forward and backward, I'm in the same state, right? At least mechanically, I'm in the same state, right? Did my hand or my body expend net energy? Okay. Here's Desfontaine. By the way, he goes by DDF. Sorry, it's big D, small d, and then F. Sorry. That's the book. When I push on the book, okay, there's a force downward, but that doesn't do any work, right? Because I'm moving perpendicular to that force, right? And then there's a force that I first push this way, but I have friction, right, pushing back to me. So I'm delivering work to the book. And then when I go the other way, the friction just turns around, right? And again, still pushes back. So I'm still doing work on the book. When I come back, it's not like I'm getting energy back. Okay. So that led historically to an enormous dilemma, right? Things that you now take for granted were not taken for granted when people try to prove conservation of energy. Because if you do this example here of me rubbing on the book, you wouldn't think energy is conserved, right? Because like if you have a purely mechanical perspective, hell, energy is not conserved because I'm losing energy whatever I do. It's like, right? I'm losing, I'm always losing, right? You see my point? Forget about everything you've learned. Put yourself back into the 1700s and you do this experiment. You don't think energy is conserved. Hell no. It's like, whatever I do, I seem to be losing energy, right? And why is that? What am I missing? Why did I do this completely silly example? What's the missing part of the differential? Okay, now I need an answer. And I'm fainting. I heard it somewhere. So it comes out of space here. Yes, go ahead. Say it again.
Heat.
Heat. Yes, thank you. Heat is the missing differential, right? So work, mechanical work is not a conserved, is not a total differential. The total differential, so now I'm going to write it as del W because we finally have arrived, right? Work is not an exact differential. You're missing heat. The two together are an exact differential. And they will be because they will be the differential of the internal energy, right? This is the net energy balance going in and out of a system. And so why was this such a problem? Well, this was a problem because people, you know, in the 1700s had no clue what heat was. I mean, they know it was a thing, but they had actually had no idea that it was just some other form of energy. So whenever they did measurements, right, because they tried to back up statements with measurements, they could never, ever prove conservation of energy because they were missing part of the differential. And that's why I did this silly example, right? So if you don't know what physics is going on in your system, you can't actually quantify energy conservation. So maybe I have only like 8 minutes left, so, but a very brief history of heat, because it's actually kind of funny. You could learn from it for today's science. So Laplace, and by the way, that's the same Laplace from Laplacian and other annoying math. Laplace in the late 1700s, so he was 1750 to 1850. Wow, he was 100 years, really? God, I hope that's not an error in my notes. I got to check that because otherwise Laplace became 100 years. He had something called the caloric theory. And that's where the word calorie comes from. He thought that when you transfer heat between two bodies, let's say two is higher, that caloric particles move. He thought heat was a form of particle exchange. And this was heavily criticized by a dude called Scheele, because Scheele said I can radiate from a fire on a distance, right? If you stand from a fire, it's really kind of nice, right? And so Scheele said, well, you know, you can't do radiation with particles that have to diffuse. And Laplace just sort of like argued, oh, but you know, the particles are really fast, blah, 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 and therefore they sort of jump at you from the you know, the fireplace you stand in front. So Scheele didn't get anywhere. Laplace was kind of stubborn. The guy who figured it out was Rumford. And Rumford did a classic experiment where he put a bowl of water, I think, on a balance, and then he put a weight there, and he put it perfectly in balance, right? And then I think he made the water hot, and then he cooled it down, and the balance perfectly stayed in place. So he argued, well, if particles are leaving when the water's cooling, then the balance should flip. Okay, you're all going to be like famous people in science. You're Laplace. What's your answer? Laplace is very headstrong.
That the caloric particle is massless?
Yes, that was exactly what he argued. He said, you know, they don't have any mass. They're like neutrinos, right? So, but in the end, Rumford won, and it's through an experiment that I'll, well, maybe I have time to show you. He did the famous cannon boring experiment where he learned actually to calculate, and I'll show you the real text later. So let me actually give you some history of Rumford. Maybe I'll show the cannon boring experiment. I'll just give you the history because he was quite a character. He's my famous thermodynamics person, Rumford. He was born in Massachusetts, in Woburn actually, and he was a fairly common descent. But he was quite a climber in life. He was quite the opportunist. He married, so he lived during the Revolutionary period in the US. He married the army of an colonel, and then he himself became a major in the American Revolutionary Army, except that he started spying for the British. So when they found it out, they kicked him out and they sent him to England. And you know, him being the opportunist, what do you think he did? He started spying for the British. Sorry, for the Americans, not against the British. So after the Revolutionary War, he came back to the US, hung out here a bit, and then he ultimately went to Bavaria. For those of you, if there are any Europeans among you, Bavaria is sort of part of what's today Germany, but was very powerful at the time. And he started working with the Bavarian army, and that's where he did the famous cannon boring experiments, because the way a cannon at the time was made is like you would cast a giant ingot, like of cast iron, but then you had to drill out the bore. That's why it's called the bore, because you bore it out. So they put the cannon on its, like straight up, and they put a bore in it that sort of drills down and makes the, like the bore, right? Through which the cannonball is going to come out. And he put the cannon in a bunch of water. And then had horses go around. The horses would draw the bore. And he used that experiment. He literally made the water boil just from the mechanics of boring the cannon because there's so much friction. So he had to do that because he was kind of like responsible for arms in the Bavarian army. And he got all these fancy titles. He became Count Rumford of the Holy Roman Empire because of his success in cannon boring. But when he got older, he went back to England and he founded the Faraday Institute. So he hired Davy, who's a famous electrochemist, and Davy is the guy who hired Faraday. So there's a line from Rumford to Faraday. But his biggest sin was when he died. When he died, he left all his money to Harvard, which is a much better story to tell when I was at MIT, teaching at MIT, because there are competition next door. What I'll do next time is show you a picture of Rumford, because quite a handsome dude. He was also quite the womanizer, which is how he somehow made it in life, it seems. So I'll show you the original text of the cannon boring experiment, which is quite spectacular, how he did the signs at the time, and it will give you a sense of how difficult it was to actually formulate the first law. Okay, cool. Have a good weekend. If you have any questions or comments on how the lecture is going, like I said, we're all kind of like experimenting here. So feel free to send them to me or to the GSIs. And otherwise, I'll see you on Monday. Cool.